One of the interesting things that is kind of buried a little bit, if you will, in the jTIPS thin bed modeler is the ability to independently control the three scenarios. So as a default, as you know, we have three conditions: the wet, oil, and the gas. And we define the wet, and fluid substitution takes over and produces our amplitude versus incident angle, our AVO synthetics, our wedge models, cross plots, everything looking at wet, oil, and gas conditions with the only thing we can vary on the fluid substituted cases are the water saturation levels. Now, one of the things we can do is we can make these beds actually independent beds altogether. And the way we do that is we go to Model, and there's a button called Reservoir Controls. We're going to pick that. And by default, you see here we have Reservoir 1 is wet, Reservoir 2 is oil, Reservoir 3 is gas. And that's the default behavior of jTIPS. Now let's say I just want to create three different models, and I want to understand, say, the difference in the effect of Poisson's ratio on a particular model. I don't want any fluid substitution. What does a model look like, and how do things compare when my Poisson's ratio is different? So what I'm going to do is I'm going to change this to custom. Now the minute I change the wet reservoir 1, I change from that wet condition, we automatically remove the fluid substitution capability for the other two. So I'm going to click custom, and you'll see now reservoir 2 and 3 are also custom. Don't worry, if we ever want to go back, we just go wet, oil, and gas and make them all the proper fluid substituted properties. But for right now, we're going to come in here and we're going to change these. And I'm going to call this condition A, and the next one I'll call condition B, and I'll call this condition C. Now when I hit accept, you'll notice as we get here we have on our input menu we have wet, reservoir, oil, gas, and over here in our synthetics, wet, oil, and gas, and that applies and extends to the wedge models as well. But when I hit accept, you'll see all of that changes to condition A, B, and C. So now that's what we're comparing, three independent cases. Now the other thing you'll notice is that in condition B and C, now we have to define and control all three parameters: the P wave, the shear wave, and the density. There's no more water saturation because it really doesn't matter, because this is just a condition of a bed, and so we're not performing any fluid substitution. So as we look at the system right now, there is no fluid substitution going on. Don't worry, we can always get back to the default. So what I'm going to do is I'm going to, first of all, turn off the computed shear wave for the condition A, and I'm going to change that shear wave to 4,000. 4,000. Okay, and we'll get to that reason. So condition A, I've got a P wave of 8,500, shear wave of 4,000, and density of 2.2, and that's producing this rather benign synthetic over here. So I'm going to go to condition B, and I'm going to make the P wave and the density the same. So they're 85, and they're 2.2. But what I'm going to do is I'm going to change that shear wave to 4,500. Okay, so what has that done? So we look right below here, our Poisson's ratio has gone from 0.358 in condition A to 305 in condition B. Now in condition C, I'll keep the P wave the same. I'll keep the density 2.2. And then I'm going to go from, I've gone from 4,000 to 4,500. You can probably guess I'm going to jack this up to 5,000. Okay, so now I've got a Poisson's ratio of 0.235. So what I've done is I've defined a bed with these parameters, and the only thing that's different is my shear wave. So fundamentally what I'm saying is, what happens is my Poisson ratio goes from 0.35 all the way down to 0.235. The colors don't imply gas or oil or water conditions anymore at this point. It's just condition A, B, and C. And so I can look at my amplitude versus incident angle. You can see the significant difference as we get to the far offsets. And we can see almost a different classification of AVO as a function of only changing the Poisson's ratio. And I'll jack up our trace gain a little bit, and you can see quite a significant change in the AVO curve. So this really kind of just, it's a nice little study tool at this point to say, geez, my Poisson's ratio changes. As it gets lower, I can really see this impact out on the far offsets. So let's go back to, let's say, oh, this is making me a little nervous. I like the fluid substitution. So I'm just going to go to wet, oil, and gas. All right. Now we're back to wet, oil, gas. As I change the parameters in the wet condition, everything else comes along for the ride. Okay, so there's no danger here in changing these controls. It's just a nice little way to do some studies. Now there's kind of an intermediate mode. So we've done one where it's pure fluid substitution, and we've done one where it is 3 independent beds. Let's say I want to compare what does the model look like. I'd like to look at a wet condition, a fizz gas condition, and a gas condition. How would I do that? Because I can't really do that very easily in the default model. So I'm going to go back to the model, Reservoir Controls, and I'm going to keep the wet as it is, and I'm going to change the oil. I'm going to call it, I'm taking its custom, and I'm just going to, for right now, I'll call it condition B, okay, because we really don't know too much about it. All right, so now if I change the wet reservoir, I'm going to turn the shear wave back to compute. If I change that, any properties here, okay, you will, if I change it, notice that the gas fluid substitution is being performed. You see these values change. Meanwhile, condition B in the middle is completely independent. It doesn't know anything about the other two conditions. It does know about the encasing medium and the pore properties where applicable, and of course it knows about the wavelet, but it doesn't know if it's wet, oil, gas, fizz. Really doesn't know. But what we wanted to do was, what is a gas condition? So right now I'm looking at a wet condition up here, and if I substitute gas at 30% water saturation, that's what it would look like down here. But what if I want to put it at 90% saturation, which is a fizz gas? Here's what we're going to do. We're going to take this gas reservoir. It's a couple step process here. And we recall as we increase this, once we get above 50%, we turn it to pink fizz gas. And I'm going to just type in 90%. And so now what we have is a wet condition, a completely independent thing. Who knows what's going on here? And then a fizz gas condition down here. Now, I want to make this middle bed have the same properties as this fizz gas. Well, how do I do that? Oh, very simple. I know that if it's fizz gas and I've got this velocity as a wet reservoir, that my velocity is 6804 feet per second for fizz gas. So I'm going to come here in the middle and I'm going to say, all right, you're 6804. Your shear wave is 4044. And your density would be 2.21. Okay, so now condition B, we'll see we have the same properties here. The lines line up, and that the condition B and the fizz gas are exactly the same. All right, so what we've done is we've said we let jTIPS tell us what a fizz gas situation would be like, and we forced it to be in here condition B. So now what I'm going to do is I'm going to come back to my fizz gas. Now I'm going to change this back to 30%, which is a more reasonable gas charge model. So now I have a wet reservoir, condition B in the middle, and then our gas reservoir. But I know that these properties are the same properties as fizz gas, because remember, they don't change. So I'm going to go back just for the sake of being able to view this. I'm going to change the name of condition B to fizz gas. Okay, so now what I have, and the labels change. I have a wet, I have a fizz gas, and I have a full gas charged. And we can see the difference as we look through here. The red being a gas charge, in this case a green being fizz gas. Now the one thing we can't do is change the color. So in this example, fizz gas is green. But this is a nice little way that we could sit there and do any kind of comparison we want in a roundabout way. Now the thing to be careful at this point, I've got, oh great, this is fizz gas. I'm going to go change my density of the wet curve. Okay, my gas changes. Let's go something that's a valid fluid substitution. But this is no longer really fizz gas. This is not the fizz gas condition. This one's just staying there in a stable format until I change it. So if I bump this up, the P wave up to 10,000, okay, and I have those values. Now my gas reservoir comes along for the ride, but that's not fizz gas. If I want it to be fizz gas, I'm going to type 0.9, put it in there, and then I'm going to retype these values that are now fizz gas in here. And 5252 and 2.263. Okay, now this is fizz gas. Now I'm going to take this back to 0.3. Okay, so I've done the same thing. So now I have a wet condition, a gas condition, and a fizz gas for a different set of wet reservoir properties. So that's it for this little overview, but the reservoir controls are something fun to play with. And again, when you're ready to go back to normal, you just go to Model, Reservoir Controls, and make sure Wet, Oil, and Gas is selected. And now I'm back to the good old fluid substitution controlled by the jTIPS thin bed modeler.